When we use remote sensing to study wildfire, we can do it in two relatively distinct ways. If we have an active fire, we can often see it in satellite imagery. So the simple idea is just we have land surface, we have a fire. I'm not very good at drawing fire, obviously. That's a fire. And we have our satellite up here. And we usually do this with thermal infrared remote sensing, which we can use to map the temperature of the surface of the Earth. So obviously fire is hot, so this area here is going to be hotter than this area over here, which is not on fire. So that's relatively simple. And in a situation like this, that works well, and that's all we need to do. If you imagine, though, that we have another fire over here, it's my awful fire drawing, and these fires create a lot of smoke. So maybe the smoke from this fire comes up and blows with the wind over here. Well, thermal infrared remote sensing, it looks at the temperature of whatever it's looking at. And if it's looking at the smoke that's covering the other fire, then it's going to map the temperature of the smoke. And smoke kind of cooled down quite a lot, partly because it's not actually the fire itself, and partly because it moves up into the upper layers of the atmosphere where it can cool down. So in this kind of scenario, we could easily imagine that thermal infrared remote sensing would not allow us to see this second fire. If we want to use remote sensing to direct fire crews around, we want to make sure we can see all of the different fires that are in an area. Thankfully, shortwave infrared remote sensing at around 3 to 5 microns is pretty good at looking through smoke, and so we can actually use that to still see the fire that's underneath the smoke. And there's enough of a signal from the heat of this fire that it'll actually be detectable in those 3 to 5 micron wavelengths. So we have these tools. Relatively speaking, mapping active fires it's well known how to do it. It works well. We have operational fire products that we can get globally every day. We know where all of the fires are reasonably well. In addition to mapping active fires, we can also map an area that has burned after a fire, and we can try to assess the intensity with which that burn happened. So to do that, we need to look at what healthy vegetation looks like, and in comparison, what vegetation that has burned partly or completely looks like. So we're going to look at the spectral signature of vegetation. As usual, we draw a spectral signature with the reflectance here, the wavelength down here. And I'm going to draw a little bit further into the shortwave infrared now. So we have the visible wavelengths over here. We have blue, green, and red here. And then when we go into the near infrared, we get this big bump up to around a 50% reflectance. And if we continue going into the shortwave infrared, we get two dips like this here. This one dip here is at around 1.4 microns, and the other one is at around 1.9 microns. These two dips here, they exist in the spectral signature of healthy vegetation because water in the leaves is very good at absorbing wavelengths at 1.4 and 1.9 microns. So what happens when an area burns is that it loses water, obviously, and these dips, they become shallower and shallower. We can use a vegetation index to try to assess this effect. This is called the normalized difference water index. And it is calculated with the near infrared reflectance minus the shortwave infrared reflectance in one of these dips here. So we can imagine we're using the 1.4 micron reflectance here. And this is also a normalized difference. So we divide this by the near infrared reflectance plus the shortwave infrared reflectance. So this works very similarly to the NDVI, except instead of having the red wavelengths, we're using the shortwave infrared wavelengths. This is also called the normalized burn ratio. So I will call it NBR here. What happens when an area burns is that we get these shallower dips. And when we get the shallower dips over here, we get higher shortwave infrared reflectances, and that means a decrease in NDWI and a decrease in NBR. So one thing we can do when we want to assess how intensely an area has burned is we can calculate the NBR, or the NDWI, for the area before a fire, and then we can calculate it after the fire. So we get something that looks like NBR before, and we can subtract the NBR after. This is called the difference in NBR, or dNBR. The dNBR, if we map that for an area that has burned, we'll notice that it's actually related to a variety of things that can be observed on the ground. This could be, for example, the proportion of trees that are left standing after the fire, the soil moisture in the area after the fire, and various other vegetation parameters that can tell us something about how the vegetation is going to regrow.